Good evening everyone, good evening from Hong Kong. We are really happy to welcome you today for all our friends, for friends from Europe, Asia, Middle East, here from Hong Kong. I'm Olivier Segura, I am the Managing Director for the School of Jewelry Art, and I'm really happy to be tonight with Eloïse our dear friend, but also director from the Mineralogy Museum Paris School of Mines. Thank you for joining us. I know we have many friends behind the screen, many colleagues also. Our dear moderators and interpreters are here with you for all your questions. Unfortunately, we cannot see all your texts, all your questions live, but we will receive some of your questions and answer all of your questions after our talk. If we are here today with you, dear Eloïse, is to talk about this incredible exhibition and specimens you bring with you from Paris.
That's correct, yes. We brought a bit of the Paris School of Mines Mineralogy Museum all the way here to Hong Kong for a few months. And we brought with us some really good specimens, I think. They're going to be missed at the museum, that's for sure. And the most probably spectacular one we brought over is the one that is just...
Yes, not me, here.
No, you don't belong to the museum. This piece belongs to a museum.
Exactly, we are here just at the entrance, at the starting point of the exhibition in our facilities, in our campus here in Hong Kong. And you decided to start with the one, you have it also on the screen, which is unusual, amazing for the size, for the quality, for the nature of this stone specimen.
That's correct, and we have the chance to see it live here, so it gives you the size of the specimen here. And so the bowl, it's a bowl of pyrite. So pyrite is the most famous mineral because it's really much appreciated of collectors. But usually pyrite makes cubes and not spheres like this. So this is highly unusual, and it sits on the nest of white quartz, and it's completely natural. Nothing has been shaped, fastened by man, which is the most extraordinary part of this specimen here. And it's so exceptional that it actually comes from only one mine in the world, that is the Bolted mine in Romania. Only there you can find such spherical pyrite specimens. But in this size and really perfect sphere, I have to say it's one of a kind.
It's really unique, and the exhibition will open this weekend, but we have the chance to welcome some friends and some colleagues already here in Hong Kong, and everyone is so amazed, impressed by the size of this sample.
Correct, and that's actually brings us to explaining the further introduction here. It's kind of an introduction to the entire exhibit because it gives you the hints of like what is a mineral, what are they shaped like this. So this is how we begin our journey with the minerals.
Thank you again, and we decided to start this presentation, this conversation, as we used to call it, with these 3 points. First, to start talking about the etymology, as it's quite important, of course, to define what are the names we are using, minerals, crystals, rocks, for example. Then we will dive into your amazing and incredible museum in Paris and to understand how it was created and when it was created. And we will have some time to talk about this program, this journey you prepare for us here in Hong Kong. And if you are nearby, of course, you are very welcome in these 5 steps through the minerals to understand for us, for our visitors, why and how minerals are so important for us, for humanity, for the humankind.
Correct.
So let's start our first point with etymology.
Yeah. We thought it was very important to actually set up the bases, the basic information regarding minerals, rocks, gemstones. It's those words that we're going to be using in the exhibit and here throughout this talk. So we thought it was really useful to begin with this. So bear with us for a few seconds, just the time we put the mind into frame here.
Yes, and starting with, I don't know if there is no order, but let's start with minerals. Minerals, of course, which is the base of all our specimens we have here.
That's correct, and minerals are actually the building blocks of pretty much the earth in general and rocks in particular. So what is a mineral? So a first thing to know about minerals, they have to be natural. Natural, so that means that anything that is created by man in a lab cannot be called a mineral. It can be called a crystal, but not a mineral. Then it has to be inorganic. That means that inorganic, it's not something that is living, it's something that is actually solid and completely
inorganic.
Inorganic, yeah, exactly. And it has to be crystal. So that crystalline part is the most difficult part to understand. We're going to go through that a bit later on, but you can see in this picture here that you have some atoms that are perfectly arranged into a structure, and that's what defines a crystal. It's perfect arrangement of atoms. So that's the concept of mineral. We have the mineral, a natural inorganic crystal.
And we will talk a bit about this sample later because you bring it here, and this is also quite exceptional. After the minerals, we wanted to talk about the rocks. Rocks, what is the difference? What is the difference between minerals and rocks? What is a rock?
To be simple, honestly, a rock is just an aggregation of minerals. So the definition is really easy on that one. And I think that everybody knows the rock called granite. You have one example here on the right-hand side, and if we zoom in here, yes, you see that granite is made of several different minerals. You can see the black dots that are the mica, you can see the whitish pink that are feldspar, and you can see the kind of the gray ones that are quartz. So three kinds of minerals constituting the granite rock, if you want. So that's pretty typical.
So here it's quite obvious. It's eye visible. You can see the different grain, but it's not every time the case.
No. Some rocks have so tiny grains, so tiny minerals that you can't see them with your eyes. For example, limestone that everybody knows, the calcite crystals making the limestone are so tiny you cannot see them with your eyes. And actually on the left-hand side, it's even more obvious here. You have obsidian that is not even crystalline. It's actually natural glass that was created during a volcanic eruption. The lava froze down, if I can say that, but had to solidify so fast that it didn't have the time to crystallize much
organize the atoms.
Correct.
Yes, that's quite impressive to see this samples. They are not with us, so you need to visit your museum in Paris.
Or just look at the landscapes around you.
Yeah, exactly, thank you. Our next point is to talk about gemstones. Of course, at the School of Jewelry Art, and you know we have a lot of lovers of jewelry pieces. You know the gemstones, so to define a gemstone, it's something which needs to be beautiful, durable, and rare. So beauty, durability, and rarity are the criteria to define a gemstone. So it could be usually a mineral. For example, here on the screen, you have a lot of different minerals, different nature. Tourmaline, probably, some quartz, I don't know them all, but a bunch of, yes, all tourmalines we have here, different colors of crystals, we can call it gemstones. But as you say, rocks, with all the diversity of colors, of textures, of patterns, also are very suitable for jewelry pieces, and you can cut it as a cabochon and use it. And we have here we call it more ornamental gemstones. And here you have also great selections. These are not tourmaline, but charoite, lapis lazuli, rhodochrosite,
turquoise, malachite.
Turquoise. So yes, a vast diversity of gemstones. When we talk about gemstones, minerals, we need to talk about also the science and the mineralogy of
those items, yeah. So it dates back, minerals were known, have been known in nature forever, since human exists. But the one who really understood what a mineral was and the different kinds of minerals that existed is Pliny the Elder. So that dates back from over 2,000 years ago. He wrote an entire book just describing the different kinds of minerals. For us in mineralogy, that was kind of a foundation book for mineralogy onwards. And really after that, the other book that came for us as a big marking time for mineralogy is the book by Georgios Agricola, who is called De Re Metallica. And that went further than just looking at minerals, but he looked at rocks, he looked at ores, very important rocks that had chemical elements that could be used by mankind. So in that book, you go even further with mining as well. So of course, as a School of Mines, very important for us. And that dates from 50-56.
Yes, so that's quite impressive to see the evolution and how the men always wanted to classify, to order the nature and to understand the nature. And this brings us to one very famous man that we know when we talk about mineralogy, when we talk about crystallography.
Correct. Yeah, I mean, another turning point for us is, well, René Justahui. He was the first curator of the Paris School of Mines Mineralogy Museum actually in 1794. And he was the one who actually understood the concept of minerals as crystals. And we're going to go back to the slide very, very quickly. But he was the one who actually understood its intimate nature. By looking at this calcite crystal that he has in his right hand in the picture that you have here, he has this calcite crystal, and it's thanks to this calcite crystal that he broke down, but not on purpose. He broke it down while he was analyzing it. And by breaking it down, he realized that the crystals obtained, that the fragment obtained, had exactly the same shape as the original crystal. And thanks to that, he understood something very important, is that all minerals are made of a primitive shape that can be deconstructed over and over and build up together to make up the minerals. So he wrote down that into a treaty of mineralogy in 1801. So again, for mineralogy and specifically crystallography, the turning point was 1801 with the decree by Aui.
Can we say that is why now you cut many calcite when you visit? If you visit the Mineralogy Museum in Paris, you will see Eloïse cutting calcite to explaining to your visitors.
Yeah, we like to break calcite at the museum, and I'm sure if you come and you get the guided tour, you will have one of us breaking calcite for you. And if you're lucky, you actually can do it yourself.
Yes, and that's also why we love, as a gemologist, René Justahui, because we can say also it's a kind of beginner talking about precious stones, about gemstones. When he wrote this Traité des pierres précieuses, this precious stone treatise, that we are really lucky to have it one sample in 1817, in which he talked about the properties of precious gemstone.
And how to determine them.
And how to do the difference in between all the gemstones. So it's a kind of the beginning also of the gemology and the way to give a name to the different stones you can have. When we talk about mineralogy, we saw that men really wanted to classify, but mineralogy is obviously a science.
That's correct.
Very complex science.
Right. So in 1801, I mean, the abbot, René Justahui, didn't understand everything. I mean, the concept of atom was not really understood at that time. We had to wait until the development of X-ray diffraction to be able to understand what matter was and to kind of see the atoms thanks to X-ray diffraction. And on the right-hand side here, you see one of Lawey's experiments, and that was in 1912 only. And it's Laurence Bragg who actually was able to understand what was those dots. And that he realized that, okay, these are atoms, and those atoms are not randomly arranged, they're perfectly arranged to form what we call a crystal. And crystals, and in this case, a mineral.
Yes, that's really impressive to understand, because they don't have the physics behind what they are seeing. But to interpret, thanks to these tools, X-ray diffraction, what is behind, every time struck me. And we talk.
That's still how we define actually new mineral species. It's thanks to X-ray diffraction plus the chemical composition.
Right. And when we talk about gemology, it's even a younger science. And when we want to study the crystal or to see the gemstones, we have to test. Of course, we cannot destroy and we cannot crush, and we cannot do X-ray diffraction on the jewelry pieces. We have to test. That's why we use non-destructive tests and tools, usually based on optical properties. On the left, you have some tools very commonly used by gemologists, and that you can use also when you come to l'École School of Jewelry Art. You can test by yourself these tools, refractometer, spectrometer, for example. But when you go to the lab, to the gemological laboratory, for example, the LFG, French Gemological Laboratories in Paris, they use more research instruments like Raman spectrometer, infrared spectrometer, different kind of tools, also based on optical properties, chemical properties, physical properties, to determine if the stone is natural or treated, the nature, of course, of the stone, but also it gives a lot of information about the treatment, in case there is some treatment, but also for the origin of gemstone. As you know, that origin is a very important topic for gemologists.
All right. I think that defines pretty much our topic today. So
yes. So let's talk about this incredible School of Mines and Museum of Mineralogy. Yes. With a few words, I think we have a short movie by Didier Nectou, our dear Didier, who is the co-curator of this exhibition we have here in Hong Kong, but is also the former director of the School of Mines, a Museum of Mineralogy, and I think we can launch this short movie.
Again, bringing you a bit of Paris to Hong Kong.
Nous sommes en plein centre de Paris, dans le 6e arrondissement, au 60 boulevard Saint-Michel très exactement. C'est là qu'est l'école des mines, dans l'hôtel de Vendôme. Mais il y a un merveilleux trésor caché, le musée de minéralogie, qui abrite une collection qui a été fondée en 1794 par le Comité de salut public. Il s'agissait de faire l'inventaire des ressources minérales de la planète. On peut admirer plus de 4500 échantillons pour une collection qui contient 100 000 pièces. C'est la 4e collection mondiale en matière de...
I hope the quality was enough. I know sometimes there is a problem. Is it okay, moderator? Quality, no problem? Perfect. So thank you. And every time, during these few seconds, Eloïse told me you are all very welcome to Paris to visit by yourself the museum.
Yes, it's an amazing collection, and we have to trace it back a bit in time. So to first talk about the School of Mines, Mines Paris PSN nowadays we call it, but it dates back from 1783. The school dated back from 1783, and it was created under King Louis XVI, who realized the importance of having some engineers, some mining engineers in France. We had like really important natural resources in France back in that time, and still nowadays actually. And we realized that it was not good enough to actually bring the engineers from all over from Germany. The School of Mines in Germany existed just a few years before, but we had to create our own like engineers. So that's why it was created, and those engineers were the ones who would be able to find natural resources, to understand where to find them, and also to mine them. Plus, not only to mine them, but who would be able to understand how to extract the interesting elements and to transform those interesting elements into useful pieces of our everyday life. So that was really the purpose. On the right-hand side, you see this decree, the royal decree, and on the left-hand side, where we were at. To begin with, we back in 1783, we were at the Hôtel de la Monnaie, which is actually a place that you can still visit in Paris. It has its own museum.
Yes, that's quite impressive to see this monument. Still, you were not occupying the whole building. Yeah, because it's really huge. On the next slide, we talk about the cabinet mineralogy.
So yes, in 1783, what happened when the School of Mines was created is that the director had its own collection to teach the students. But during the French Revolution, we understood that that was not enough. A mineral collection was good, but it didn't have everything we wanted to talk and to teach the students. We wanted to have the products of the mines of France, of course, but from all around the globe. And that kind of collection we need to preserve all the time and over the years, to preserve it for future generation. So not only we were preserving the ores of those mines, the minerals, but even the byproducts, meaning that sometimes the rocks were not really useful at the time, but we should preserve them to actually, maybe in the future, we know how to use the chemical elements in the rocks. So that's why the collection was created in 1794. And you see on the right a catalog. Everything that entered the collection was catalogued. And on top of that, of course, you have the rocks next to them with the catalog number. And this is this ugly rock that you see on the left, but really useful rock, as it's a main iron ore here.
Yes, that's why it's amazing to understand that museum and the research collection are not only for the past, but they are for the future. And thanks to our ancestors, researchers in the past, now we, all our researchers and university can work on this collection because your collection is still alive.
Yeah, we have researchers coming very often. I mean, just last week we had someone who wanted some very specific ores inside and like chemical elements, such as, for example, like silver. Silver is highly strongly used. So a collection is still alive, not only for the public, but for researchers as well.
Yes, do we say how many minerals you have in your...
just a few 100,000, yeah.
Yeah, so I think you can find what you are looking for. And if we are back now to 1815.
Yeah, so I mean, so the collection was created in 1794, and the first curator was René Just Ahuy. Again, Ahuy. Yes, he was the first curator there back in the day, so a big discovery about what a mineral was, a crystal was, is date that back in the time. And we were actually not, we moved from being at the Hôtel de la Monnaie, we moved all the way to the Hôtel Mouchy that doesn't exist anymore in Paris. You know, the French Revolution was a period that a lot of things happened, you know. So we moved on there, and why is the Eiffel Tower in between?
Yes, this is my question.
It's because
which was not existing at that time.
No, but his name was so important that it had to be inscribed on the Eiffel Tower.
Yes.
So we remember we had to commemorate his name, his person, by writing it on the Eiffel Tower.
And so important is on the first a name inscribed on the Eiffel Tower, so it shows, it demonstrates how important this man was for our science and for the science in general. That's quite important. And sorry, I was just a bit in advance, but now we are in 1815 in the Hôtel Vendôme.
Yeah, so that's the definitive place. I hope that is going to be the last one. Yeah, but we've been here since 1815, and you look at this pretty picture. It shows, it's a very actual picture. It shows the facade of the Hôtel Vendôme. So this hotel was a private mansion to begin with, and it was the Duchesse Vendôme. So maybe that rings a bell to you.
Yes, we know her very well.
Yes, Vendôme is a big name of the French royalty. So she was the first one to live there in 1708. 1708, so the beginning of the construction is really early on. And it has been a private mansion for years, decades, until the French Revolution. So during the French Revolution, this beautiful house was seized from the royalty and was attributed eventually to the School of Mines, who has been sitting there since then. But you know, it was a private mansion. That means that it was not great to welcome a school, not great to welcome students and labs. So we had to trick and do a few arrangements. And if we go to the next slide, you will see what has been done.
Yeah, just before maybe the next slide, if you visit Paris, of course, we are in Jardin du Luxembourg.
Yes.
Amazing place.
That's correct.
Sunset is unbelievable.
Beautiful. On the right-hand side of the picture, you see the greenhouse of the Sénat, of the Luxembourg garden, yes.
And this is a great postcard you find.
Right. And it dates back from the mid-19th century. And what you see is the floor for the Mineralogy Museum that was still available for people to come and to see.
First floor?
Second floor.
Second floor.
Second floor of the Hotel Vendôme. And so not only teachers, students, but also outside visitors already back then could come and visit the collection. So you see the wooden floor, you see the perfect like wooden cabinets. Just bear with me, because on the next slide you will see what it looks like nowadays.
Yes, yes, yes. That's quite impressive to see it from the past, but today,
pretty much the same.
well,
we removed a few rocks because it was really crowded. We added lights, but it looks pretty much the same. This picture was taken actually at nightfall, and I wanted to show the sunset. It's a beautiful time to visit the museum. Sunset is just amazing.
This wonderful light. And you told me that also it's protected by decree. You cannot modify.
That's correct. It's a heritage of France.
Monument.
So that means that all the wooden cabinets that you see is part of the French heritage, and the collection is a national collection, so it's protected as well.
And you wanted also to show some different view, like when you enter, you start your visits.
When you start your visit, it looks like it's a small museum. You know, you have those two small rooms, dark, with impressive specimens. They're large, they're beautiful, but then you don't realize that when you come into the museum, you're going to actually see 5,000 specimens of minerals, of course, but rocks, gemstones, meteorites, synthetic crystals. And that's spread out throughout the museum. But in total, in the collection, we have 100,000 specimens. So it's a huge collection with a large geodiversity. And the picture that you see on the right-hand side of the screen here shows that everything is ranked by chemical and by species, by mineral species. So we have over 1,000 different species shown to the public. That makes us one of the best museums in the world for the variety of species we display to the public.
Yeah, so that's why. After visiting the exhibition in Hong Kong, you need to travel to Paris to see the vast diversity. And we wanted to introduce also this window, this showcase with the French crown jewels.
Yeah, but that's just a teaser for people to come to Paris. You know, we don't want to talk too much about the French crown jewels because the history.
Yeah, so to prepare your question.
Yeah, it has a lot of history back there. Like we don't have much of the French crown jewels in the national collections anymore. So.
Yeah, very interesting point. And our last chapter, we want to go together through this journey you prepare through minerals, through mineralogy, through these incredible samples, and just again to show the importance of the minerals. We live, I as a geologist, we live since childhood grabbing some gravels and our past, but for everyone to visit, to understand these 5 different chapters you created. And we started with the first one, which is this journey through matter and why minerals are so important to understand or to explain matter.
Yeah, I mean, they are so important to our everyday life, but before going into that scene, we wanted to show what a mineral was. And you know, I think that the first thing that is striking is some minerals can show so perfect faces, perfect angles. It looks like it was something that was man-made. And no, it is not. So that's the first journey we wanted to bring people to explain that minerals are composed of chemical elements. Sometimes, and most of the time, it's several different kinds of chemical elements. And on top of that, those chemical elements are arranged into perfect shapes. And these shapes, this arrangement that you see at the atomic structure, sometimes is reflected at the macroscopic scale, and that's the case of this beautiful pyrite crystal coming from Navarone in Spain.
Yes, and sometimes if you visit some fair, some mineralogy fair, you can find it 1 centimeter cubes. That's amazing, but here the size is just, that's the difference in between a private collection and the museum. But we go quickly to the second showcase, because this is also pyrite, but it's not cube. So why?
It is cubes. Can't you see cubes there?
No, I cannot.
No, okay. So actually, if you look deep down in the atomic structure, if you look with a very strong microscope, electronic microscope, you will see that in the intimate structure, what makes these crystals are also piling up cubes of iron and sulfides that make up the pyrites. Think about a Lego that has a cube shape. Well, piling up cube Legos, and you can make plenty of different shapes, and that's the case. That's what happens with those pyrite specimens here. So for for pyrites, pyrite crystallizes into the cubic system, but actually that's not the case for all minerals. There are actually 7 different kinds of, I would say, shapes, or most likely crystallographic systems that appears in nature. And
Are
here,
we going to the next one?
yes, we can go into the next one because
I just had a comment. I just think that I hope all our kids playing with Lego will become mineralogists.
I hope so as well.
Yes, yes.
And in the exhibit, we actually have the opportunity to show 3 different crystallographic systems. The second one we're presenting is the rhombohedral system, explained with calcite. We have this beautiful specimen on the left, perfectly transparent, that shows off this rhombus kind of shape that you see here. And again, like pyrite, calcite can do many different shapes from this primitive rhombus shapes.
That's really fascinating. And we just go to the next one, which is an apatite.
Correct. With the third shape that we wanted to present is the hexagonal shape, hexagonal crystallographic system. You can see on the left blue apatite that is used as a gemstone, by the way.
Yes.
And what you see at the macroscopic scale, you can see at the atomic scale on the right, the different atoms that compose apatite are hexagonal in shape. They make this overall hexagonal structure.
And again, you need to come and to see the size. Thanks to the nice picture from Benjamin Shelley, we can have a good understanding of this mineral and the shape of this mineral here. Our next chapter, and the one you want to propose, is maybe the one we know more, and I know many friends of us know very well, of course, the use of crystals for jewelry. So this journey through jewelry start, of course, with gemstone, but you wanted not to start directly with gemstone, but something
gemstone is too obvious, you know?
It's a bit obvious, but with the metal, because maybe we forgot that metal is also a crystal.
So the base of your piece of jewelry is metal, and metal, you have to extract the metals from the ground, from minerals, and the obvious one is, of course, gold. And you see on the left-hand side here, a beautiful piece of gold. It's completely natural, it has not been faceted, and that's stunning. So gold can not only be a metal, an alloy,
yes.
It can also be an atom, and it can be a mineral.
Which is really the tricky part with gold, the name gold, the word gold.
I know.
Which is different reality.
And that's the case for gold, but also for copper, silver, and tin that are used in your pieces of jewelry. Now we can move on to the main obvious ones, I would say.
Of course, we talk to the gemstones. And gemstone, what makes a good gemstone we can use in jewelry, because there is many crystals, in fact.
Yes, I mean, we have 6,000 different mineral species. How many do you use as gemstones?
Not so many. Probably
why is that?
Probably 100, maybe, with designer, creators.
Yeah. And why don't you use them all then?
That's a good question. We need to talk to our designers. But obviously, we need to talk about the properties and the physical properties, because we need to wear the jewelry, and obviously as a ring, when we wear every day, for example, rings, they can be damaged. So we need to talk about the hardness and the toughness, 2 very important physical properties. The hardness is resistant to scratch. For example, here on the right, you have a tourmaline, which is heavily scratched, even if it is a quite hard material. And to distinguish the different hardness of materials, Mr. Moss created this scale, so it's a relative scale index. Maybe you know that diamond is the hardest material, 10 on this scale, so only a diamond can scratch a diamond, and you have this scale from 10 to 1. We used to say that for jewelry, we use crystals and minerals from 10 to 7, to quartz. Why is this 7? Because quartz is the most common crystal on Earth, and many dust particles are made of quartz. So it means all the dust, maybe rubbing or scratching slowly, your jewelry pieces are made of quartz. So that's why it's better to have more than 7 to have a really good gemstones.
Mm-hmm.
If we talk about the toughness, so the next one is the resistance to the break. And if we take the example of the diamond is 10 for the hardness, but not 10 for the toughness. Because we can cut diamond, and because we can create really cleavage plane, use the cleavage plane to cut the gemstone. Since antiquity, And you see here in the center this very specific gesture of the diamantaire with preparing the diamond with the diamond knife, with the diamond hammer, preparing on a very specific plane. And you see on the right this very specific cleavage plane to create this perfect like cut, very perfect facet of the diamond. So toughness and hardness is very important. Obviously, and of course, when we talk a gemstone, we want our gemstone to be beautiful. And we are really lucky here because you brought really beautiful gemstone, beautiful rough.
Yeah, I'm actually glad. You know, I'm proud of this beautiful piece of beryl. And when the beryl is that color, bluish color, we call it aquamarine. So this is a beautiful piece of like rough aquamarine that you just saw here and that is presented on the left-hand side. And you see this is a natural specimen, meaning that all the faces are real, made by nature. The top is like kind of standard, but it's natural, and the face alternating from smooth to a bit depolished, completely natural. The color, the transparency, you can cut a lot of gemstones out of this one, but, but we saved it, we rescued it from being cut. It has been preserved as a rough specimens. But I have to say that some pieces of cut material I love, and that's the case for this Dom Pedro aquamarine that you see in the center here. It's over 10,000 carats, so it's really large. It's a really large piece of gem, and it has been cut mostly on the backside to create this beautiful pattern. It's amazing, but I think that's kept at the Washington D.C. Smithsonian Institution. And maybe you can cut on the, we can talk about the one on the right that is...
Yes, because we can also, for jewelry pieces, some designers, some brands and maisons decided to use also like a rough or just slightly polished to reveal the rough. And you see here it's still a beryl with a green part, which is emerald for the green beryl. And here they decided to keep it like rough to develop and to show really the power of the earth, maybe, in this design with the dragon. And if we go on the next showcase we have here at Hong Kong, we talk about the ruby, which is part of the corundum family.
Correct. Corundum, when it's red, we call it ruby, and we brought with us a special corundum. So, of course, the ruby here that you see on the left-hand side doesn't have the transparency, doesn't have the clarity. However, it has the color and it has the shape. And on top of that, it's on the white background, like white rock, and which is actually marble. So it tells the story of how this ruby was made. That's why we wanted to bring it over. And of course, we have two beautiful examples here of pieces of jewelry with the ruby inside.
Yes, it's so amazing to have more than 20, let's say more than 5 carats. It's already very rare. More than 10 is extremely rare. More than 20 doesn't exist. That's so rare to have more than 20 carats. This quality, transparent, vivid. And maybe, I don't know if you notice for our colleague here through the screen, maybe you see on the right a very small dot inside this Carmen Lucia ruby, which is an inclusion, a very small inclusion. But no matter, when we talk about color stone, we talk about color. The most important is the color, and this size, this transparency, this color, even if there is a small inclusion.
I love it, actually. I love this inclusion. It tells you, it's its signature. It tells you about the geology, but I'm not going to go into that.
Maybe it's a mineralogist ring.
Yes, I would love to have it.
It's for you. Me too. I will love you have it. And if we go to the next showcase, we talk about garnet.
Of course, we think about garnet as red in color, but what we brought over with us is actually what we call more Fanta garnet because of this orange, bright orange color. Look at this beautiful piece. It looks like a man-made piece again, but these are garnet crystals on the host rock. That is just amazing. So garnet can come in all different colors. It can come in red, of course,
all
but
colors
green,
except blue. Even if there is some now color change with blue.
The purple, but I like the pieces of jewelry as well, using the Fanta garnets over there.
Yes, and again, thanks to all your researchers and your work to save and to preserve these samples because it's so beautiful. And obviously, the jeweler, more and more designer, creator use this garnet because it's tough enough, it's hard enough, and obviously the color is amazing, Fanta. because Fanta, when we talk about Fanta, everyone has this color in mind because everything, I think, everywhere in the world you can drink this Fanta. And you see here, for example, Jar decided to use it in a small stone, like to depict really the peeling of the peel of the orange. And here on the right, this incredible Van Cleef & Arpels necklace with orange garnet that you can see in some patrimony exhibition.
And of course, we cannot talk about gemstones without talking about jade, especially in Hong Kong. And for that purpose, we brought this large piece of jade slice on the right that you see. It's 90 centimeters high and only 3 millimeters thick. So it was difficult to carry all the way back from Paris, I can tell you.
That's why we cannot talk to you before it was installed.
No, I was very stressed. That was the first piece that we installed when we first arrived here. And on top of that, it has a lot of history because it was part of a trophy that was given to us by Jean-Pierre Alibert, who was a French explorer. He discovered the graphite and jade deposits in the Ural Mountains, and those deposits have been actually mined back in the mid-19th century. And not to forget his name, he gave some trophies back to some famous French institutions, including the Paris School of Mines. So the left photos that you see is at the bottom of the staircase of the museum. This trophy was there, and if you look at the top of the image, you see that there is a slice. The top of the image, you see the slice. It's exactly the same slice that we brought over to you.
Yes, also thank you, Mr. Alibert, to have this piece now in Hong Kong, and thanks to our dear lenders, because we are able also to show some exquisite jade. Of course, in Asia, you know jade, you love jade, and you have the opportunity to see this imperial green jade, or even this lavender jade, which is really also amazing. On the next chapter, you want to go through technology and the importance of minerals for technology.
Yeah, it is a very important chapter. I know that you're arriving at the end of this lecture, but we wanted to highlight the fact that we use minerals in our everyday life, right? Take a cell phone, for example. A cell phone is, you have to extract 40 different minerals to actually make your cell phone, from the electronic component to the screen to, I mean, all the parts of your cell phones are used geological materials at least. And what we wanted to show here with the copper crystals is that, I mean, copper has been used since the ancient time, the Copper Age, then the Bronze Age. And actually, if we would back in time, the Flint Age, men to go hunting, they use flint, so they use rock for the entire time. So this piece of copper here is completely native copper, meaning that it's completely natural, and that's why humans were able to actually use them, fasten them, and transform them to make useful tools. And still nowadays, copper is a strategic element used in wires.
Exactly, everywhere around us we have electricity.
Okay, and in wires, in electric wires, like such as this one. So it's everywhere. And on top of that, nowadays, copper is strong. It has been always a strategic element, but nowadays, with the transformation with the cars, using electric cars, copper, we need 5 more coppers than cars before. It's very strategic.
More and more copper. And what we learned, thanks to you, is that we find coppers not only in copper.
No, I mean, when you mine copper, it's not copper as native elements. It's so rare in nature that we would mine copper ores. Though that's a mine in New Mexico, and you see the color is more oxidized, it's reddish, and actually the rocks that you will find are those rocks that would be green to blue in color, and that are copper ores, such as azurite on top and dioptase on the bottom.
So a huge and long and complex process to extract the
Correct.
atoms from these minerals.
Yeah, and copper was just an example, but it pretty much works for every kind of elements.
Our next chapter, your next chapter, is the journey through arts. And this maybe we don't need to talk a lot because you bring incredible samples. The one on the left is a sepiolite.
Yeah, that's correct. I mean, this one, you just have to look at it. The left specimen is natural clay nodules. The thing that we did is to remove the outer crust, the mud that was around the clay, to reveal the sepiolites, the sepiolite nodules, just the clay atoms. clay rock. I mean, it made us think, like
Yes,
Didier,
it looks
especially
so
the
nice.
co-creator, thought about this Willendorf Venus kept
Yes,
at the museum.
maybe our friends through the screens know this piece, or maybe they know also this other piece by Fernando Botero.
Right.
So who is influenced by?
Maybe you're going to see something else in this, this
Yes,
natural
exactly.
piece of art.
And you bring also this one. Oh, this one is probably my favorite, but it's also your favorite.
It's my favorite for so many different reasons. It's a volcanic rock that has opals, different kind of opals inside it. But when you look at it, wow,
Yes.
what do you see? You see two eyes, a nose, a face. Look at this, and different kinds of opals inside.
Yes, that's so. This close up, and thanks again to the incredible image by Benjamin when he came to visit.
That's Laurent Carif, actually.
It's Laurent also. Sorry,
Yeah.
I don't want to mistake. So dear Laurent, when he visited
The museum, and you see the opals. You see the left-hand side with precious opals with their iridescence, and the right one that is a fire opal.
Yes, and when we were discussing is, I asked you, but does Jean-Michel Basquiat visit your, or did Jean-Michel Basquiat visited?
I mean, the
Your
piece was
museum?
there with this
80,
rock. Yeah, this
1990.
rock arrived in in the 1970s. So yes.
So maybe, who knows? Our last chapter is a journey through space. And when I received your proposal, I say, but why do you want to talk about space? There is so many minerals on Earth.
Yeah, I mean, of course, everybody knows that rocks and therefore minerals are the building block of our planet. But on top of that, minerals are the big building block of the entire solar system. When you look at this representation here, you see dust particles that accumulated as grains, grains that can accumulate as rocks as asteroids, and sometimes even by gravity you can have larger bodies such as planets. Yes, and all of this is floating in the solar system, and you know some planets formed and eventually collided and broke into pieces. So you have plenty of fragments in the solar system that are floating. And you see here a presentation of those grains on the left-hand side accumulating to rocks, all the way to some planets with a core, a mantle, and a crust. So guess what? The fragments floating represents the different kinds of rocks that are in existence. If you go to the next slide.
Yes, I was to say, sometimes we have these amazing images.
Exactly. So what are meteorites? I mean, they represent actually the rocks that are floating in the solar system. On the left-hand side, we talk about chondrites, which are just grains that are accumulated, but didn't evolve. So it has been the same since 4.5 billion years ago. And the other ones are more evolved. That means that they are fragments of planets, former planets that existed, from the core to the mantle to the crusts. And what we brought to you
Yes, that's a piece of incredible siderite, a piece of meteorite.
Yes, we brought with us a core of a former planet, and it's sampled as siderites, which is iron-rich meteorites. But we brought to you only things that we could actually use in piece of jewelry. So this one here, actually, when you etched that metal part away, mostly composed of iron, it reveals some parts that are more rich in nickel. That's why you have this pattern. This pattern
very specific.
used.
You can see on the dial.
Yes, on the dial of the watch here. Really impressive.
You bring also.
That's my favorite.
Different kind of meteorites. Oh, I thought it was an opal.
No, in meteorites.
Oh, okay.
My favorite in meteorites, because meteorites are usually like gray and ugly, but this one is not gray and ugly. It's metallic with some gemstones inside.
Some gemstone inside. That's kind of, we call it peridot or olivine.
Right. They are
the
oldest gemstones in the world, 4.5 billion years old. Amazing. And that's what Jean Vendôme used in this.
Jean Vendôme, for our friends who were able to visit our exhibition in Paris, about Jean Vendôme, were able to see this necklace he made, he realized, with this palisade. But on our next and last part, we wanted to end this journey through space.
Yeah, with something dramatic, you know, like a meteorite arriving on Earth and destroying everything on the left-hand side. That's just a representation because we never saw that happening in our lifetime. But if you look at the right side here, we saw some meteorites arriving in Russia in 2013. So this is kind of small, it's okay, but when it's big, it then actually impacts the Earth rocks. Of course, everything around, like dinosaurs, they know something about it. But the Earth rocks can actually change because of the impact of a meteorite and melt away sometimes.
Energy and the heat of the impact transform the rock.
Correct, and melt away, and that's the case for the 3 specimens we present here to you. These are melted, so natural glass created during an impact with the meteorites. The most interesting one is, I think for me, the moldavite, the green, what we call impactite, and it's just beautiful. And again, it's used as a gemstone.
It could be used in some region in Eastern Europe. They use it a lot as a regional gemstone and cut it and faceted as a cut gemstone and used in many kind of jewelry. I know we are running out of time because it's fascinating, but we need to reach to our conclusion. And for the conclusion, we have it here, these samples of incredible violetish pink stone.
Yes, and we brought it to you because, of course, it's used as a gemstone. And then when it's called spodumene, but not many people know that as spodumene.
No, we call it also, as a gemologist, we call it kunzite. And kunzite from Mr. Kunz, George Friedrich Kunz, who gives the name. So, of course, if you have questions, we can dig into more. Who has Mr. Kunz, gemologist for Tiffany, who decided to use for the first maybe these gemstones, but we can find it in many different brands and jewelers. For example, here these samples for Van Cleef & Arpels, and I think it's dear to your house because it's part of the Elizabeth Taylor collection.
That's right.
Probably fits the color of her eye. So it's a great conclusion to talk about.
So of course it's used as gem, but for us it reflected the fact that it's a natural piece of art and that it's actually also beautiful and it's super useful as well because this specimen contains a lot of lithium. It's a lithium silicate. So that means that this kind of specimens, not this one because it's too pretty.
No, we keep it like that.
But that's what is looked for when you think about lithium. Lithium is a strategic mineral, and we think about it because it makes up the lithium batteries, car batteries. Of course, our cell phone batteries, but the car batteries have been changing our look of lithium. We need to mine lithium so much more than we need to mine lithium only a few years ago. Look at this car, and that's the floor of the car that takes most. Yeah, the battery that is made of lithium. So sometimes the batteries weighs more than 200 kilograms, which is huge. And that's why we need to mine lithium.
Exactly, and you even find a link with space.
Yes, because, men have been mining the earth for thousands of years. And eventually we're going to run out of elements. We're going to run out of interesting ores if we don't recycle. So we have to be mindful of the fact that we are mining the earth. On top of that, what we are considering doing is, as we are mining out the earth, we might want to explore and to go and hunt and mine some asteroids and find some other elements or some elements that are not reachable inside the earth. We would go and mine them on the surface of other planets and asteroids.
So that's really a great samples to sum up all this journey through minerals. We have 5 minutes more. I'm sorry for that, but I'm sure it was quite interesting. We don't see all your comments, and thank you so much. I know you are very so many to follow our different talks. I need to have a few words before the questions about obviously our video credits. So you will find all the information in our YouTube channel for the next presentation. I need to talk to you also about the next conversation online. So you will have a great presentation about the writing jewels. So new and great topics by our friends from Paris, I think, if I'm not mistaken. But it's now time for the last minutes we have together to receive your question. And to receive your question, I'm really pleased to welcome on stage our dear Anne, who is our moderator and who selects some of questions for us from your side. Thank you, Anne.
Yes, thank you very much. We received very many questions. So the first question is, are we still discovering new minerals today?
Oh, great.
Yes, and the answer is yes, and many. And actually, about 100 specimens, new mineral species are discovered per year. And that's not because we are hunting new places, it's because the technology advanced and we have better tools like we talked about X-ray diffraction. X-ray diffraction has advanced and we can look into tiny little grains, tiny little specks. So we're opening doors of museums. And we look at rocks and we look at specimens much smaller than we were able to do before. And this way we can actually refine the structure, know the chemical composition, and define new mineral species, yes.
So you mean it's not a dusty science?
No.
So there's still many researchers. And you told us that there is some PhD and some new researchers working with the
yes, collection, yeah. The
collection,
research.
yes.
So we mentioned about the hardness of 7. So we have one question asking that a stone cannot be considered as a gemstone unless it has a small hardness of 7 or higher. Would it will be break if it is less than 7?
Well, there is many question in one. So in fact, yes. Definition of gemstone, we say, is beauty, rarity, durability. But it's not really a very specific concept where we have a border in between the different hardness. We propose this number of 7, which is the more suitable, the more easy to use. But in fact, and you know more, some nerds, some collectors, some people, they love gemstones. They can use different kind of gemstones. Some faceters, we have some friends, stone cutters, they manage to cut gemstones with a hardness of 2 or 3, which is unbelievable. Yes, you have here, we have a great example of fluorite.
Which is so soft, and so like
there is
not hard at all.
Cleavage.
And cleavage plane everywhere, so it has the worst of all, and it's still used as a gemstone. Some people are crazy enough to cut them and to even wear them. So you would actually not wear them in a ring, you would wear them in necklaces, for example.
Yeah, so I think there is no limit to the creativity. There is the stones for gemologists, for mineralogists, but usually if you want to have the largest or the most suitable gemstones, ruby, sapphire, emerald, of course, what we call the precious, many garnets, tourmaline, topaz, usually there are more than 7 in hardness.
Yes, I think we still have time for a few more questions.
Of course.
So another question is, what are the criteria of a new samples in the collections of the museum?
Very interesting. We have only 2,800 species in our museum over the last 6,000 of them in existence.
Yes.
So that means that we still need to acquire a lot of new species that have been discovered over the last tens of years. So first, we need new species. Second, we will need new localities. You see, you will experiment throughout the museum or here in this exhibit that depending on the geological environment, therefore on the locality, you will have, the specimens will show off different faces, different look, different crystallographic and mineralogical association. So we always want different localities so it's more representative. They will have more or less impurities. So new locality. And of course, if it's a specimen that we have already, if it's a specimen from a locality we have already, but if it's better looking, we'll take it.
You can change it.
Yes.
Okay, maybe it's time for the last question. And this is a long one. So what is the future of gemstone considering the economic challenges? So are we still going to see a decline in the demand?
Decline in demand.
Decline in demand. I'm not sure there is a decline in demand, but maybe a decline in the offer, as it's more and more difficult to find large and nice color gemstones. For example, there is up and down in different mines. For example, a few years ago, if you ask for some Fanta garnets, it would be easy to find Fanta garnets, very orange, deep, vivid garnets. But some depleted mines, and now it's very difficult. So if you ask me to find a Fanta garnet or to create a jewelry piece with a Fanta garnet, it's very, very difficult to find. So we are really working with minerals, with objects created by nature. So we don't know what we will find tomorrow. We don't know what we will find after tomorrow. So it's always a matter of resource. So we cannot predict the future. Of course, there is more and more science behind this, geology, mineralogy, so also geology to understand where are the different mines. But well, it's very difficult to predict the future.
And if I may add just something, is that the fact that first of all, your jewelry is recyclable, that the metal is completely recyclable, the gemstones themselves are recyclable. So it's always something that if you want something new, you don't have to buy something new, you just can create, ask a new jeweler to make something new out of your old piece of jewelry.
Yes, you're right. We didn't talk about the crown jewel, but it was the case.
Yes, exactly. That's exactly why. And on top of that, I think that the demand makes the fact that we are opening our minds to new mineral species used in pieces of jewelry as well. And it's not only the famous ones that we're going to be used, it's going to be some different ones as well, which are sometimes pretty and more affordable, so it really depends on what you love. I love garnets, for example. Garnets is everywhere, you know, it's not the most fancier, most expensive ones, but they show a variety of colors and that are just amazing to me.
Yes, you love all the cubic system.
I love cubic system.
Is it our last question?
Yes.
Thank you very much. Thank you, and thank you all, our moderator, interpreter. Thanks to all our friends behind the screen. Thanks to all the team to be able to realize this live broadcast. Thank you so much. See you very soon online, on live, here in Hong Kong, in Paris, in the campus of l'École, or at the Mines
Museum, of course.
Thank you very much.
All right, bye.
Thank you.